Hi everybody, this is Dr. Niger with the Chem Calculation screencast. This screencast is going to look at how to determine the formal charge on an atom within a molecule and how we can use the formal charges of the atoms to determine the most structurally stable molecule. All right, so let's start with this formal charge. All right, we're going to represent that with FC in our formula in just a minute. All right, it's a hypothetical. And I don't mean it's unreal. I just mean that it's different than an ion charge. It's a hypothetical charge, all right, that we're going to assign to an atom. I keep putting an I in atom today. An atom within a molecule. All right, and again, hypothetical because it's not like we're going to write carbon plus 1/2. All right. It's not an ionic charge in that the electrons have been fully transferred, right? But it is based on how an atom shares its valence electrons within a molecule. So we're going to be interested in how many valence electrons an atom has, and then how is it using those in the molecule? Is it sharing them in bonds? Is it keeping them as lone pairs? All right, so we're going to need to know both of those pieces of information. So we're going to end up comparing the valence electrons on a lone atom to how it shares those electrons within the molecule. All right, we are going to make one assumption though. We're going to assume that electrons within a bond are shared equally. All right, we're not going to worry so much about polarity here. In other words, we're going to keep those electrons shared equally in the bonds. All right, so let's start with the formula, how we calculate the formal charge. We need three pieces of information. All right, the first thing we need to know the number of valence electrons. All right, so we're going to need the periodic table. All right, once we know that number of valence electrons, we're going to subtract two numbers from that. The first, the number of electrons in lone pairs around that atom. All right, and then we're going to look at half the number of electrons in bonds. All right, now the number of lone pairs electrons, it gets all of those because they are only associated with that particular atom. But the bonded electrons, it only gets to count half because it's half theirs, half the other atoms. All right, now keep in mind a single bond has 2 electrons, a double bond has 4, and a triple bond has 6. So make sure that if you have multiple bonds attached to your atom that you're keeping track of those. All right, so that's going to be our formula that we're going to be using. All right, the sum of the formal charge values for a molecule, must equal the charge on that molecule. All right, so if you have a molecule that's neutral, like carbon dioxide, then when I calculate the formal charge on the 2 oxygens in the carbon, the structure should give me an overall formal charge of 0. If it doesn't, then I have either drawn my structure incorrectly or I have calculated my formal charges values incorrectly. All right, if I have a polyatomic ion, say nitrate, all right, and I'd write the structure and then I do my formal charges and I add those up, I should get an overall formal charge for the molecule of -1 to match the charge on that polyatomic ion. All right, so that's one way to check that you've got your structure drawn correctly and that you've calculated your formal charges. Now, what can we use this for? All right, we can use this to look at structure stability. All right, structure stability Typically, you want zeros for your formal charges because that means they've used their valence electrons in the most effective way possible. All right, so typically your most stable structure will have formal charge values of 0. All right, now that's not always going to be possible. All right, so if you have a molecule, you've drawn all the structures, you don't have one that's all zeros, that's fine. All right, that's fine. But if there is one that has all zeros, that is going to be the most stable structure. All right. If not possible, then the structure with negative charge, or negative, I don't want to just put charge, negative formal charge on more electronegative atoms. Goodness gracious. The most stable. All right. Same thing with the positive charge. The less electronegative atoms should have the positive charges, all right? Because electronegativity is this ability to attract electrons. So it makes sense that atoms that have a negative formal charge are the ones that are attracting the electrons. So that will be the most stable structure, all right? So again, you have to be able to calculate the formal charges, and you're going to look at the total formal charge on the molecule. If you get all zeros for all those formal charges, that is a very stable structure. If you can't do that, then you want to look for the structure that puts the negative charges on the more electronegative elements and the positive charges on the less electronegative elements. And then that is going to be your most stable structure. All right, so we're going to practice. We're going to do a couple different problem types. All right, and these can be a little tedious, but it's really good practice. All right, so choose the best structure based on formal charges. Show your work. All right, so first thing I'm going to do, I've got 2 hydrogens and 2 oxygens. So I'm going to call this hydrogen 1 and hydrogen 2, and I'm going to call this oxygen 1 and oxygen 2. I only have 1 carbon, so I'm not going to worry about that one. All right, so for my carbon, all right, to calculate the formal charge, valence electrons, so 4 valence electrons minus the number of lone pairs, I don't have any, minus 1/2 the number of electrons in bonds, 2, 4, 6, 8. All right, so that's going to give me an overall formal charge for carbon of 0. All right, now I'm going to move on to H1, 1 valence electron, 0 formal charges, 1/2 of the 2 electrons in that bond gives me an overall formal charge of 0. Move on to H2, all right, 1 valence electron, 0 in lone pairs, and 1/2 of the 2 electrons in that bond to oxygen. So a formal charge of 0. Oxygen 1 up at the top, 6 valence electrons for oxygen. Now I've got 3 lone pairs here, so that's 6 electrons. And then 1/2 of the 2 electrons in that bond. All right, so I'm going to get a formal charge here of -1. All right, and then I look at that other oxygen that's down next between the hydrogen and carbon, 6 valence electrons again, 1 lone pair, so 2 electrons there. Whoops. And then 1/2, and I've got 2, 4, 6 electrons in bonds. All right, so that's going to give me a +1 formal charge. So those are my formal charges for that molecule. I'm going to come over to my other one. Again, I'm going to label the different hydrogens and oxygens, and then I'm going to repeat. All right, so I start with my carbon, 4 valence electrons, no lone pairs, 1/2 of the 8 electrons in bonds, so a formal charge of 0. H1, 1 valence electron, no lone pairs, and 1/2 of those 2 electrons, so formal charge of 0. H2, 1 valence electron, 0 lone pairs, 1/2 of those 2 electrons in the bond, formal charge of 0. All right, O1, it's up top, 6 valence electrons. Now this time I have 4 electrons in lone pairs, and then I get 1/2 of those 4 electrons in that double bond, which is going to give me a formal charge of 0. And then O2, 6 valence electrons, 4 electrons in lone pairs, and then 1/2 of the 4 electrons in those 2 bonds, formal charge of 0. All right, so if you look, you can see over here, oxygen has formal charge of -1 and +1, where on the other structure, zeros. All right, so here we have formal charge all 0. This is going to be a more stable structure. All right, so if I were to draw this molecule, it would look like this. All right, so that's going to be more stable than the one on the left. Okay, so that's an example of how we can use the formal charge if we're given structures to identify the more stable. All right, now down here, for each molecule, draw the possible resonance structures that the molecule, assign formal charges in each, and then circle the most plausible structure. All right, so if I think about this structure, probably gonna have an O, a C, and an N. All right, I've got 16 electrons to work with here. All right, so double bond, whoops. And then we'll just share the double bonds. We'll just do this. All right, so there's one option. All right, now if I think about it a little bit, let's say O, C, and I know nitrogen likes triple bonds, so maybe I'll move one bond over here and move a lone pair. So we'll do this. That's another option. Oops, I didn't leave myself very much room for my brackets. Hold on. All right, let me fix this. There we go. Sorry, I had to put my charge in there. All right, and then I guess I could do the other triple bond on the oxygen, carbon, nitrogen. So 1, 2, 3, 4, 5, 6, 2. All right, so there are my 3 options for my resonance structures, moving the multiple bond around. All right, so now we're going to use formal charge to figure out which one is the most stable. So I'm going to start with oxygen. So it's going to give me on this side 6 valence electrons minus 4 minus 1/2 of 4. So this is a overall formal charge of 0 for the oxygen. All right, carbon in the middle, 4, no lone pairs, minus half of the 8, 0. And then nitrogen, 5 valence electrons, minus 4 in low pairs, minus half of 4. So this is going to be -1. All right, so that's one set. All right, so we do oxygen again here. It's going to be 6 minus 6 minus 1/2 of those 2. So that's going to be -1. And then we're going to have 4 minus 0 minus 1/2 of 8. So carbon is still 0. And then nitrogen is 5 minus 2 minus 1/2 of 6. So that's going to be 0. All right, and then we go to our last structure. Oxygen is 6 minus 2 lone pair electrons minus 1/2 of 6. So that's going to be +1. And then carbon is 4 minus 0 minus 1/2 of the 8 bonded electrons. It's going to be 0. And then nitrogen has 6 lone pair electrons this time, minus half of the 2 in the bond. All right, and that's going to be -2. All right, so these are our choices. None of them are all 0. All right, so I can't use that. So now what I really need to think about is electronegativity. All right, according to the periodic table, the most electronegative element is fluorine. And then it slightly decreases as you move, well, all right, so technically electronegativity increases as you move across a period towards the halogens. So if we stay up in that row, we've got fluorine, oxygen, and nitrogen. So oxygen is more electronegative than nitrogen. All right, with that in mind, oxygen should have a formal charge that is negative compared to nitrogen. All right, so if I look, all right, right here, here's oxygen. It's positive, and here it's negative, and here it is 0. All right, so I automatically am going to say no to this structure because oxygen is more electronegative than nitrogen, so it should be negative over nitrogen. So this isn't a good structure. All right, over here, I've got nitrogen as a negative versus oxygen being 0, or nitrogen could be 0 and oxygen could be -1. All right, well, because oxygen's more electronegative, this is going to be the better structure. All right, nitrogen can be -1, it can have a -1 formal charge, but not if oxygen's at 0. Oxygen is more electronegative, so it makes more sense for oxygen to be pulling the electrons towards itself. All right, so the structure that is going to be the most stable of these three is going to be this one right here. Okay? All right, let's try another one. All right, so this one's carbon dioxide. All right, so we have 16 electrons here. All right, so we've got two choices. We know carbon's in the middle. All right, so we can have one lone, 2, 3. We could do it this way and put a triple bond to this oxygen. That would use up my 16 electrons. Or I could have a double bond between both oxygens and have this structure. Either of those are plausible. All right, now you might say, well, why don't I do the triple bond on the other side? Right, because that's the exact same molecule. It's just flipped over. All right, the bonds are the same. The number of lone pairs are the same. So you only need to draw it once. All right, so I'm going to call this oxygen 1 and oxygen 2. 1 and 2. All right, so formal charges. Oxygen 1. All right, so we've got 6 valence electrons, 6 electrons in lone pairs, and then we get half of those 2 bonded electrons. So that's going to give us a -1. All right, for oxygen 2, 6 valence electrons, 2 electrons in lone pairs, and we get half of those 6 bonded electrons, so that's +1. All right, and then carbon 4, no lone pairs, and half of the 8 bonded electrons. Carbon's almost always formal charge 0. It likes it that way. All right, now we look at oxygen 1 in our second. We've got 6 lone pair electrons, 6 valence electrons, 4 lone pair electrons. Right, and then we get half of those 4 bonded electrons. Formal charge is 0. All right, O2, same thing. 6 valence, 4 lone pair electrons, and then half of the bonded electrons. Formal charge is 0. And then for carbon, 4 valence, no lone pairs, minus half of those 8 bonded. All right, so you can see here all formal charges are 0. This is going to be most stable. All right, so this time, this guy, right? Which makes sense. If you think about oxygen has 6 valence electrons. It's got 2 electrons that could use a partner. So it likes to make 2 bonds. So structures where oxygen can make 2 bonds are going to be those where it's going to be the most stable. All right, one more, N2O. All right, so I'm going to treat this just like carbon dioxide. Nitrogen, oxygen, nitrogen. All right, I'm again going to have 16 electrons to work with. So one option is going to be 3 lone pairs on one side and a triple bond on the other. And then I could do the 2 doubles. Whoops. All right, so that's an option. So let's call this nitrogen 1, nitrogen 2, nitrogen 1, nitrogen 2. All right, so N1, 5 valence electrons. I've got 6 lone pair electrons, and then half of those 2. All right, so that's going to be not plus 2. What am I doing? Minus 2. Yeah, minus 2. Sorry. Second nitrogen, 5 valence. 2 lone pair electrons, and then 1/2 of the 6. All right, so that's going to be a formal charge of 0. All right, and then oxygen, 6 valence electrons, 0 lone pair electrons, and then 1/2 of 8. So this is going to be +2. Oh, it seems like a whole lot of formal charge, but let's see. All right, so we'll slide over to this one. So N1, we've got 5 valence electrons minus 4 in lone pairs minus half of the 4 bonded electrons. So that's a formal charge of 0. That already looks better. All right, nitrogen 2, 5 valence, 4 lone pair, and half of the 4 bonded, also 0. All right, and then for oxygen, we've got 6 valence electrons, no lone pairs, and then oh, goodness gracious. Can I do math today? Apparently I cannot. All right, 5 minus 4 minus 2 is -1. Sorry about that. 5 minus 4 minus 2 is -1. All right, minus 1/2 of 8. All right, so 6 minus 4 is +2. So this is what we have. Yuck. Neither of those look fantastic. I mean, they're both terrible because nitrogen has the negative charge and oxygen has the positive charge. So that tells me that neither of those structures are good ones. So I can't put oxygen in the middle. I think that that's what it's going to come down to. So neither are great. Try again. All right, so what do I mean by try again? I'm like, try a different order. All right, so let's put a nitrogen in the middle. So nitrogen, nitrogen, oxygen. All right, so I still have 16 valence electrons. All right, so I could do 2 doubles. All right, so that's an option. All right, I could nitrogen, nope, nitrogen, oxygen. I could do a triple over here and a single over here. So that would be a structure that's electronically okay. Nitrogen, nitrogen, oxygen. I could put the triple over here. All right, I think those are my 3 options. All right, so again, this is going to be nitrogen 1, 2, 1, 2, 1, 2. All right, so we'll do it again. Nitrogen 1, 5 valence electrons, 4 lone pair electrons, and then 1/2 of the 4 bonded. So 5 minus 4 minus 2, -1. All right, nitrogen 2, 5 minus 0 lone pairs minus 1/2 of those 8. All right, so this is going to be +1. And then oxygen, 6 minus 4 minus 1/2 of 8. So this is going to be 0. All right, well, that's not awesome. All right, let's look at this one. So nitrogen 1, 5 valence electrons minus 2 lone pair electrons minus 1/2 of 6. All right, so that's going to be 0. 5 minus 0 minus 1/2 of 8. So this is going to be +1. And then oxygen is going to be 6 minus 1/2 of 8. Nope, not 8, sorry, 2. All right, so 6 minus 1, -1. That one's better. All right, let's look at this one. So nitrogen, 5 minus 6 valence minus 1/2 of 2. All right, so 5 minus 6, so that's -2. All right, then nitrogen, we've got 5 minus 0 valence minus 1/2 of 8. So this is going to be +1. And then oxygen is going to be 6 minus 2 lone pair electrons minus 1/2 of 6. So this is going to be 6 minus 5. So that's also +1. All right, so if I look at these 3, all right, my best choice is going to be this one in the middle. All right, I've got a negative formal charge on the more electronegative atom compared to the other 2. And I've got a positive charge on the less electronegative atom compared to the other two. So this is going to be my best bet, this one right here. All right, and it's because negative on, formal charge on oxygen. All right, so this was a good problem because if I were to draw my Lewis structures the way I normally do, particularly since I just did CO2, I would put that oxygen in the middle, but clearly that is not where it belongs based on the formal charges. So because there was another option to put a nitrogen in the middle, redraw them, look at all my options, and the most stable structure is going to be that one in the middle, all right, where the triple bond to one of the nitrogens, single bond to the oxygen. Now the oxygen is not super happy, right? It would rather have the double bond, but it's okay. All right, so again, formal charge can be calculated if you know the valence electrons and you have your structure. So you know the lone pair electrons and the bonded electrons. It's hypothetical in that it's not a full transfer of electrons, but it can be used to give us an idea of which structure is going to be the most stable.